Okay, so I'll introduce Yilin today, and Yilin Wang is my PhD student. He's a second year PhD student, and he graduated from Tongji University as for a bachelor degree, and then Carnegie Mellon to get a master degree. And he's doing research related to traffic signal control, traffic state estimation, using both model-based and machine learning-based approaches. And he is actually a very good cook. He and he's very serious about that. And sometimes I feel like he's as serious as cooking, comparing to doing research. and and actually, he did not put it here. He's also a very good piano player. Wow. And if you have a chance, you can listen to him playing. And also think that. Oh, and by the way, I never see him dressing like this. So he must prepare a lot for today's presentation. Okay, so floor is yours.
Yeah, thanks for the introduction from Professor Feng. And there is one. Oh.
We need to take a good picture since you're just.
Thank you. Actually, when I start cooking, I become bigger and bigger every day. So, yeah, I guess it's my sort of be cooking well and improve my cooking skills. So, hello everyone. Today, my presentation is about a connected vehicle-based signal priority system. And today I think that most of you have attended last week's demo, and today's presentation is just a continuous, detailed explanation on the last week's demo. And I will start with the introduction, which is also an overview of our project. So the name of our project is named Smart Intersections. So the objective is that we want to pave the way for national deployment of connected automated vehicles, and this project is also supported by USDOT with $9.95 million for 3 years grant. So what we will do in this project is that we want to install a smart intersection that has both has the smart sensoring and edge computing device, signal control system, and also the CV2X and the SRC communication system. Some related applications for this project is that about the traffic signal priority and the emergency vehicle preemption, which is mostly related to the traffic signal control, and the priority request optimization. And also, we will apply the dynamic signal optimization through this framework. And the last application for this project is a green wave speed advisory, which will mostly provide the driving guidance for the drivers when they are approaching the intersection, like give them some advised speed based on the current signal timing and the planned and optimal signal timing for saving the fuel and eco driving. And today I will introduce the transit signal priority and emergency vehicle preemption application, since it is also a public service application. And the motivation between these two applications is that we want to reduce the travel delay for the public transit, especially in the congested traffic intersections. For example, see the pictures on the left. It is totally a deadlock in the intersection during the peak hour. And we think that since the public transit holds more passengers than the private vehicle, so we might need to provide a higher priority to the public transit. And also, we are thinking about the emergency vehicle preemption because we want to ensure the safety and clearance ahead of their route when they are approaching a congested intersections. Because there are a lot of crashes, and according to the statistics, about 46% of the emergency service provider was killed on their way to their destination. They killed by the car accident and the collisions. And this is also one of the news happened in the state of Connecticut, and which is two fare trucks was collisioned in the intersection at the intersection. So basically, this is the motivation for these two applications. And then I will introduce the model and the framework of this application of this project. So before start, I want to introduce a multi-model intelligent traffic signal system, which in short called MITS. I will call it MITS in the following of the presentations. So it is a connected vehicle-based traffic signal control system, and this is the GitHub page for that open source application. And it is also can support the adaptive signal control and multiple traffic signal control models. And also it's used for the signal priority and coordination. And the most importantly is that this framework can support the JE2735 DSRC message set, which is quite important. And we think that this kind of message is a standard message that could be furtherly deployed in the field, in the real world. So for the architecture for the MITS can be divided into two parts mainly. So first part is for the vehicle side, and the other part is for the infrastructure side. The both two parts is connected. They talk each other through the radio or the wireless application like DSRC or CV2X in the future. So I will start from the vehicle side. So basically, for the vehicle, it will if your current vehicle is a connected and automated vehicle, it will generate the host BSM. Or if it is currently just a normal human driving vehicle, we can access this BSM from the GPS from the current vehicles. And anyway, after we have the host BSM for the vehicle, and the vehicle will talk to the infrastructure to get the map, which is predefined in each infrastructure, and it is sent through the radio to the vehicle, and the vehicle side will determine whether it needs a priority and sends a priority request, which is in short named SRM, which is the signal request message, and it generates the SRM based on the BSM and map. And also the spec means the signal phasing and timing from the infrastructure side. And for the infrastructure side, once it receives the SRM, it will send the SRM through the RSU, which is roadside unit, meaning for the communication, and it will give to a request manager, and the request manager will then pass this request to the solver and then solve to the optimal traffic signal timing, and then it will send to the traffic control interface. And this is the priority solver is the most important part in the infrastructure side. So I will introduce this part detailedly in the next page. And after the traffic control interface got the optimal signal plan, it will translate those into a real signal plan and send it back to the signal controllers through the connections between the infrastructure side and the signal controllers. So this is the detailed logic for the priority request solver, and this is the most important part for the model and the framework to see how to get the optimal signal plan. And we start from when the priority request is received, and it will firstly through a question judgment part, which is that the current request emergency vehicle request. If it does, it will give the highest priority. So last week when I show everyone, show everyone is the setting when our vehicle is a public transit, which is not have the highest priority. So we will follow this part. But when the current request is from the emergency vehicle, it will just calculate what it is currently required and omit all the phase and give the highest plan. So that means when two vehicles are approaching, the lower priority, the lower vehicle has the vehicle has a lower priority will be denied when the emergency vehicle approaches. Then we will formulate all the requests as an optimization problem. And given the input of the current signal timing and the signal status and the current traffic status, we will solve and obtain the optimal plan and then formulate everything to a transportation traffic controller interface. And that is all for the whole total framework. So the next question is that how to formulate all the priority as optimal as an optimization problem. So this is the objective function for our optimization problem. It has two terms. The first one will merely consider the priority request from the vehicle side, and also what we also integrate is that we integrate the coordination priority request into this framework. So we will formulate the coordination plan in the corridor as a special request, since the coordination follows some circle, and sometimes it requires a certain times of interval to be green. So we formulate this part of the coordination as a coordination priority request. It is on the second part. So but with the summation of these two parts and the weighted parameters, so we can solve the whole problem as mixed integers of linear programming and get the optimal timing plan with the constraints of precedence and the phase duration and priority request and the coordination request constraints. So this page is about the feasible region. So we know, as I have mentioned before, we not only formulate the vehicle priority request, but also formulates the coordination request. So this time phase diagram shows what is going on for this feasible region for our algorithms. So on the bottom side, it is the time. It shows the time. That means we start from the time 0 and with the unit of second. And on the vertical side, it is mainly about the index of the phase. So firstly, we currently need to follow the precedence constraints, which means the phase has to be followed by sequence. So that's why each phase is followed here, each formulated here. And the lines here means the current signal plan for us. So which means for example, the right line here. The red line is in the phase 3. That means the phase 3 will be on green from the start of this point and ended from this point. And it means the phase 3 is on green this time interval. And the blue one and green one is just the boundary for this for this algorithm, and the space in between is the feasible region. And the determination of this boundary follows with a lot of concerns, which is not only the signal phasing duration, like the minimum green time, the maximum green time, and also we want to ensure our current our current request is being served without delay. So it also follows with the priority request constraints. That is all for the implementation and models for this framework. And then we will do some field testing and and deployment on the whole system. So we divided our deployment as 3 stages. The first one is for the hardware in the loop simulation, we bought everything and we built everything in our lab and put everything on a script on our hardware and run all the simulation. And the second stage is a test facility implementation. On this August, we drive our vehicle to M-City to test all the stuff. And then after doing that, so we think it is ready for us to do a real world implementation. So in next year, we will implement this framework on the city of Ann Arbor and Detroit on over 20 intersections. So let's start with the hardware in the loop system. So there are overall 5 devices in this system, and we have one desktop, which is mainly used has a Windows environment, which is mainly run the vSim simulation. So the objective for the vSim here is that it provides the BSM for the emergency vehicle or some other vehicle that needs priorities. But also it also provides the virtual controller, which we can show what is going on and if the controller is being served with the priority with optimal signal timing. And also we have two edge computing device, which is one for the infrastructure side and another for one is for infrastructure side, one is for the vehicle side. And also we have two conda communication device that can talk to each other. One is across the onboard unit, and another one is the roadside unit. And this is the demo video for the 2 settings. Firstly, we will set our vehicle as a transit vehicle, and it will approaching from the source to the northbound. And as you can see, current phase is the current phase is on the conflict phase, and it will force off after it reaches to the minimum break time, and then it goes to the next phase, and the next phase will still force off, and then give the priority as soon as possible. And another issue is that another example is like when the okay, so that setting is we changed the setting from the transit to the emergency vehicle. So as you can see, the signal will just give the green phase anyway, no matter what is the current sequence of. So that is the difference for the 2 modes. And then we're doing our field deployment in the M-City, and we basically set 2 connected vehicles, and this one is our vehicle, and we borrowed another one from the M-City, and the settings are the same, but we just split all the stuffs apart and install the VSP and two OBU on the 2 cars separately. So what we want to test is like we have 2 vehicles here, and one vehicle is approaching from the source to the north, and another vehicle is approaching from the westbound, from the east to the westbound at the same time. So we create a conflict request, and we want to test what is going on when the 2 vehicles are all in transit, and one vehicle in transit, another one is for the emergency vehicle. And this is the. Is that the timer? Oh. Okay, I'm almost done. So this is the demo video for the testing. So we have still we have 2 scenarios. One is for 2 transit vehicles approaching. And in this video, we have 2 vehicles, and this vehicle is approaching from the south to the north. And this is vehicles approaching from the east to the west. And on the bottom side, this is the interface for the real traffic controller which is a Econoline controller, and this is a visualized interface on the vehicle side. I think if any of you take part in the last week's demonstration, you have quite familiar with this interface, because this interface mainly can tell you what is going on your current in your current intersections, and it will show the current signal timing when you're on the map and your current locations, mainly based from the BSM, post BSM from the vehicle side, and also if your current request is granted or rejected. So in this case, in this example, the transit and the truck are rejected because emergency fire truck is approaching. So the algorithm will ensure the priority for the emergency vehicle first. And okay, so let's start with the, and when the south vehicle approaching, it will. So when a south vehicle approaching, so we can see that on the right side, the two vehicles have the sends its priority and it's being granted, and then the algorithm will let the right side one, the first one pass, and then the second one pass. And then it gives the green face to the second one. And that is for the first scenario. Second scenario is like we reset the north side as an emergency vehicle. So it is passed. So when it's approaching the intersection, the algorithm will calculate its estimated arrival time and give the highest priority to the emergency vehicle. And as you can see on the on this interface, it is that the current request is rejected until it has passed the intersection, and then it is being granted. And that's that is all when it's approaching. And it will wait until the whole cycle and escape to the minimum green time, and then it gives the green face. Okay, so that is all for our testing, and our future work is like we want to integrate the TSP and the emergency vehicle preemption with the speed advisory. So we want to integrate the whole things with not only with connected vehicle, but also with the connected automated vehicles. And also we want to integrate the adaptive signal control with cooperative perceptions in the future. And then in the we will test our next phase in the later of this November. And after we pass everything, we will deploy all the stuff in the city of Ann Arbor in next year. So that's all for this presentation, and thanks all for listening.
Signal priority system has been around for 40 years or so, buses and emergency vehicles. So your system, which I can intuitively tell it will improve, I want to hear from you. Would you tell us what will be tangible benefits of having connected vehicles, the system you are working on, or the current ways of prioritizing vehicles at intersection?
So when you think
what kind of improvements, what
okay,
changes you're making that will give us more benefit?
So our current setting in the real world is like when an emergency vehicle approaching, it will just alert this alarm, and everyone will stop its vehicle on the right side and let the emergency vehicle pass. But in fact, the traffic signal will not be responsible for that, because the emergency vehicle can pass the intersection regardless of the signal. But in this framework, if we connected the emergency vehicle with the V2 with a V2X V2I communication, the signal will respond to the emergency vehicle, and it will ensure the conflict phase. The conflict phase has the right signal. So I think that the most improvement is based on the safety concern because it can prevent some potential collision. So the drivers on the conflict phase will not only hear about the alarms, but also they can saw those red light on their current phase, and they can they can ensure.
I hopefully the students heard. I don't hear very well. I couldn't catch exactly your answer, but doesn't sound right. Andrew, well, I take your word for it.
Well, let me just add to it that when I was at your age, I've been already learning about these priority solutions, and it's not just that vehicles are just cleaned and the emergency can go at any signal. There was already solutions long ago about how to extend green, how to bring green earlier because of vehicle coming, and also for the transit units and for emergency. So just following Professor Sinha's question, what is new in this case? Because I'm not buying your idea that in the past there was no preemptive control. There was preemptive control. The controller knew, of course in the modern, knew about coming emergency vehicle or public, and there was some adjustment. So what is new in your solution?
I would like to say for the current setting and what we have done so far is not that new. But in the future, I could say there is some potential improvement because we could connect all the intersections together, and we can realize like a pre-plan for the emergency vehicle rerouting or other stuff.
So instead of quick response locally, you're talking about optimizing ahead in the entire system, preparing the corridor.
Yes, and also we want to pre-clear the route for the emergency vehicle.
Okay, I'll add a few comments to both of Professor's questions. One is, it is not more systematically the solution. The traditional transit priority or emergency vehicle preemption is usually first come, first served. Right? So it does not really minimize the impact of the intersection. This is one. And second, now we have multimodal priority. We integrate the transit vehicle. We don't show the freight here, but transit vehicle, freight, and the emergency vehicle in the same framework, so we can adjust the weight to dynamically adjust their priority levels. And the third one is this framework also integrates the coordination, which does not exist for previous TSP systems, because if the corridor is a coordinated corridor, this TSP, no matter it's TSP or emergency vehicle preemption, is disruptive to the coordination. If we treat them separately, then it will introduce more congestion. But now this is an integrated framework to consider both coordination, delay, and priority delay together.
Well, it was just to get this kind of explanation. How much we're going ahead, what we're already used to that. At least this discussed in classrooms, and I think everything was implemented what was kind of presented as the solutions. Okay, thank you.
Have you considered a scenario in which two emergency vehicles are coming from different phases, and then how do you deal with their priorities? Like if they're approaching it at the same time?
Oh yeah, actually it's could, and because the different kind of vehicle has different weight. If you remember the objective function. If you remember, if you can see this objective function, and there is alpha and beta, which is just a general weight for the vehicle priority and the coordination request. But if you do go into that, for each vehicle, it has its own priority weight based on its mode. So basically, we will follow the the optimal solution for the objective function, and then give the whole.
But like hypothetically, if there's a fire here and there's two fire stations and they're both sending out their vehicles at the same time, so they'll have the same priority at the intersection. So
Yes.
you have a solution.
Yeah, that's
for-
also based on the signal timing, the current signal timing, because even if they are reaching to the at the same time, the distance to the next phase, green phase, is different. So the algorithm will consider all the delays and give the optimal solutions overall.
Have you considered emergency vehicles not following the traffic signal? Like emergency vehicles currently, like you were saying, don't follow
Yes.
the traffic signals.
Mhm,
So if you have two emergency vehicles approaching, have you considered the fact that they might not recognize that it's a connected intersection and go anyway?
Yes, this is a very good question. And actually, it is not that considered, but it is not mattered, because if you remember this framework, emergency vehicle will be served at the highest priority, which means when the emergency vehicle is approaching and it sends to the intersection its location and current speed, the intersection will calculate its estimated arrival time, and it will just give the green phase to the emergency vehicle anyway. So I would like to say that for the emergency vehicle preemption, the objective is more like clear the vehicle ahead of the emergency vehicle, and then ensure the emergency vehicle will pass the intersection.
Thank you so much for the wonderful presentation. I'm more interested in the modeling part. So could you please tell me what is the coordination delay? Or like your optimization function, what are those terms? I'm kind of wondering, you have to be the first one is the request delay and second is coordinate delay.
Yes.
But what are they like
Okay.
explicitly?
So the coordination delay means, let me see, it's a little bit complicated to speak in one word. So it is mostly like a summation of the delay for all the vehicles in this intersection.
So it's like the waiting time, right?
Yes.
And how about the request delay? The vehicle priority request delay?
Okay. So let's see this picture here. So this diagram shows like our current desired signal plan can ensure the coordination request and also the priority vehicle request. But what if the current priority vehicle request at here? For example, if this blue box move to more a little bit later to here, and the delay and it's now served because of there is a hard boundary for the minimum and maximum green time. So there might be cut-out delay. There might be a delay for the priority vehicle, and that is what we saw. Does that answer your questions?
So the first term is especially for the emergency vehicles or something?
No. Yes, it includes emergency vehicle and the transit vehicle anyway.
Okay.
But for the emergency vehicle, it has a different weight compared to the other transit trucks.
Okay, so for all the transition, all the vehicles are transit vehicles. So what's the difference between the optimization result and the first come first serve? So, can we find out some better solutions better than the first come first serve? Any kind of this kind of scenarios if all the vehicles are transit?
You mean if all the vehicles are transit and
Yes.
they are approaching at the same time?
Not necessarily the same time, but different times.
Also, we consider the current signal timing.
Yes. So is that possible to kind of generate a first come first serve this kind of trivial solution?
It may not be optimal, right? First come first serve may not be optimal. For example, if you have a vehicle arrive for phase 1, current phase is 1, you want to request phase 4, and you need to pass, if first come first serve, and the other one request phase 3, if you want to serve for the first vehicle, right? And you may wait for a long time and then serve back to the second vehicle. But if you can optimize it systematically
So the key idea is that we cannot mix the phases. We have to go by the cycle.
If that's transit
That's
vehicles.
part of the.
Because we want to give other vehicles also opportunities to be served, right? It's kind of it's actually an equity consideration. We don't want to skip all other phases.
Because we want to minimize our negative impact on the current traffic. Also,
Just a quick question. You talked about this framework adds into the coordination, takes into account the whole coordination for the emergency vehicles. My question to you, would it be a corridor coordination, or does it take into account that the first two intersections, the emergency vehicles going straight, but for the third one, it needs to take left? In other words, it's taking the coordination from the station of the fire station to the fireplace.
it's a corridor coordination now.
It's straight cut,
Yes.
so it doesn't take third into account.
But yeah, I think it's straight now.
I have a quick question. So regarding the optimization objective function, is this used somewhere else? Like, how did you get it? Was there any other options that you like picked?
You mean this kind of structure?
Yes, like why are you using this function? What benefits does it have over other objective functions?
So.
I mean, it could be contradictory.
Yeah, I know, and firstly, honestly, I have to say, I didn't think about this question before, but it is a really good question. And secondly, I think that by the summation of structure, it may we mainly considering the linearization, because we want to formulate everything into a linear programming. So, yeah, that's what I can answer you now. But sure, yeah, I didn't think about that before.
Actually, follow question. Curious about what is the context of this research. For example, what's the connection between your method and research in existing one, or the priority control for the emergency? So can you provide us some idea about what's the main difference between your research and the previous one with the emergency vehicles and the priority signal?
So what when you mentioned the difference.
Many about the like what's the difference between this method and the previous one, or what's the like the main contribution to the new methodology or the new ideas in this entire type of
Okay.
So I think I mentioned that to the two professors' question. This is more an integrated solution that for different type of priorities as well as coordination. This is not considered in previous studies. They always consider them separately, not systematically.
So integrated in that we consider what kind of
The different type of priorities as well as coordination.
We have one more question left. Do you want to do that?
I have one short question. Do you have some statistic about the emergency vehicle and emergency vehicle crashes accident?
Do you mean the? Yeah, I think I mentioned it before. The introduction is. Do you mean the 46% emergency vehicle provider will be emergency service provider being killed, or other things?
Okay.
Yeah, that is based on the statistics.
What is the proportion in the total number of accidents every year? Because according to our personal experience, the occurrence of emergency vehicle is not very large. And
Yes.
the situation that we came across two emergency vehicles, it is much smaller. And you have some statistics in that.
Yeah. I got the first time I got the statistics, I was also shocked because I never saw two immersive vehicles crashed on the intersection. But that statistic was provided by the I think by the Bluetooth of the motor agent and through a 4-year statistic.
Thank you.
Thank you.